And we're back again with a continued video on section 7.7, Approximate Integration. This comes from James Stewart Calculus Early Transcendentals book, and we're studying techniques of integration. And in the last video, we went over some numerical methods to estimate the area under a curve between A and B for functions that we can't normally use standard techniques of integration like biparts or partial fractions or trapezoid, or trigonometric substitution, etc., to calculate exact areas. So we return to numerical methods. And in the previous video, we went over trapezoid rule and Simpson's rule to estimate the area under the curve. And I stopped because I wanted it to be a relatively short video, and this video is going to discuss how can we determine how much we're off by, what is our error if we approximate using the trapezoid rule or the Simpson's rule, and can we figure out if we're pretty accurate. And we've got a couple rules here for determining just that. Note that in the previous example or previous videos, we used a function that we could calculate the exact value of, but normally when we use numerical methods, we don't know how to calculate the exact value, so we tend to look for these error formulas to see how much we'll be off by. Good. So there are two types. There are two formulas, one for the trapezoid rule and one for Simpson's rule, and I might do a video on the midpoint rule as well, since that does appear in James Stewart's calculus text. And there are two types of problems, which is, can you calculate the error if you're going to estimate? And then the second one is, how many partitions do I need to divide my area into, and to use the trapezoid rule? How many trapezoids do I need to estimate an error that will be no bigger than a certain amount? So you can kind of guarantee that what your estimate is going to be as accurate as you want it to be. All right, so the first rule is the trapezoid rule, and ET is your error, right? That is going to be your error in estimating using n rectangles or n trapezoids, right? So we've got n here equal to the number of trapezoids. The A and B in your formula here is going to be your interval, AB, right? And you get those from your actual integral here. This is x equal to a and x equal to b. So we already have the value of n, and we already have the value of b, and we already have the value of a. So what is this k? Okay, so let's read the rule. Assume f double prime, and that is the second derivative, is continuous on AB, and k is a real number such that the second derivative's magnitude is no larger than k for all x in that interval. Then we can calculate the absolute error in approximating our integral using the trapezoid rule by using this formula. So that's how we use k. Good. And how would we normally do that? I show in the next example that I can find that upper bound, but I draw your attention towards the extreme value theorem, and that came from an application of the derivative. How can we find the maximum value on a closed bounded interval for a continuous function? We can always use the first derivative, find our critical points. What are critical points? Those that make the derivative equal to 0, right? And then we can go back to the original function and calculate f at those critical points. We also want to, on that closed bounded interval, evaluate them at the endpoints, because our extreme values or our maximum and minimums can occur at the endpoints. And so we pick the biggest output to be the maximum value. And I encourage people to review the extreme value theorem and those techniques, because we can always use that on the second derivative to find our k. We can always take the third derivative of our function, find the critical points where that third derivative is equal to 0, find those points, go back to the second derivative's formula and evaluate at A, evaluate at B, and evaluate at all of the critical points, and the biggest number output is going to be, and the absolute value of the biggest number output, so you want to consider your negative numbers as well. And you want to take that absolute output to be your upper bound for K. Okay, and that's how you can find your K. All right, so let's look at an example here. It says here it can be shown, and I show it in a second, that the second derivative of e to the x squared is less than or equal to 6 times e on the interval from 0 to 1. It then asks, approximate the integral from 0 to 1 of e to the x squared dx using T4. So that's using the trapezoid rule with 4 trapezoids. Then estimate the error obtained by approximating the integral with T4 and round your answer to 6 decimal places. I'm only going to round to 3. Sorry. Here's how. So I'm going to, with e to the x squared, I'm going to take the first derivative, and the first derivative uses the chain rule. So it's e evaluated at x squared times the derivative of the inside. That turns into a product. So when I take the second derivative, I must use the product rule. So it's the derivative of the first, which is e to the x squared times 2x, times the second, plus the first, times the derivative of the second, which is 2. I then factor out the e to the x squared, and I get 4x squared plus 2. And I see so I'm not using the extreme value theorem here. I'm not going to take the third derivative, but I do note that I've got x squared terms in that second derivative, and I note that our interval is from 0 to 1, and I know that x squared on 0 to 1 is no bigger than 1. And I know that e to the x is increasing and 4x squared plus 2 is increasing. So I'm just going to use that x squared upper bound of 1, and I'm going to plug that into my formula, and I get that y double prime is no larger than 6 times e. And that e is that 2.718, etc. And you can calculate that on a calculator. So now that I've found my upper bound k, I'm just going to plug in the values that I have for my error formula, and I see that the magnitude of my error of T4 is going to be less than or equal to 6 times e times 1 minus 0 cubed over 12 times 4 squared, because n here was equal to 4. I then make that calculation. That's 6 times 2.718, and I get 16.31 in the numerator, and 12 times 16 is 192. And so my error is going to be off by no more than 0.085, so that's even less than 1. And then it says actually use the trapezoid rule. So this is a little mini review of approximating the integral using the trapezoid rule. So remember, our first step is to find delta x, and our delta x is b minus a divided by n. And so that's 1 minus 0 divided by 4, since we're using 4 trapezoids. The next step is to calculate our x sub zeros, and 1s, 2s, 3s, and 4s, and we know that x sub 0 starts with a, and with each subsequent x sub 1 we just keep adding 1/4, which is adding delta x. Just keep adding delta x. So 0 goes to 1/4, 1/4 goes to 2/4, which is 1/2, and 2/4 goes to 3/4 for x sub 3, and 3/4 goes to 1, and 1 should equal b. Good. Our third step is then to calculate the function outputs for each of those x sub i's, being x sub 0 up through x sub 4, and our function is e to the x squared, so we break out our calculator and we calculate e to the 0, e to the 1/4 squared, e to the 1/2 squared, e to the 3/4 squared, and e to the 1 squared, and we get those approximations. If I wanted to do 6 decimal places, I could write those 6 decimal places there, but for a matter of convenience, I'm going to use 2 or 3. All right, so finally, after we've calculated all of those values, we are using the trapezoid rule, right? So this here is our trapezoid rule. And that is, we can approximate this integral using 1/2 delta x times f of x0 plus twice f of x1 plus twice f of x2 plus twice f of x3. So the internal f of x outputs get twice terms, and our last one gets a singular coefficient. So I plug in the values that I found in the previous 3 steps, and I end up making that calculation, and I get to 1.365, and I know that I'm off by no more than 0.085. All right, so Simpson's rule, if you actually compare, we've got a much bigger denominator. So look at that denominator on the trapezoid rule. That's 12 times n squared. Look at the denominator on the error estimating Simpson's rule, and that's 180 times n to the fourth. We still have b minus a, but that b minus a is to the fifth. So you kind of have to want to look at some comparisons and also the k value is the fourth derivative. Okay, so it might be hard to calculate the error on using the Simpson's rule because it might be hard to calculate the fourth derivative, especially if you end up getting a lot of product rules after the first or second derivative. And especially if you want to use the extreme value theorem, because then you're going to be using the fifth derivative to find the critical points. But here we go. Let's find the error. But I do believe that in many cases that the Simpson's rule tends to be a more accurate way of calculating. And remember that Simpson's rule requires you to use an even number of intervals. But look at the rule set. So the fourth derivative, you have to find the upper bound for k. And look at this example here. It says it can be shown that the fourth derivative of e to the x squared is less than or equal to 76 times e on 0 to 1. Then it asks you find the smallest value of n needed to approximate 0 to 1 of e to the x squared dx with s sub n up to an order of error no more than 10 to the negative 3. Then find Sn up to this order error. I'm just going to, for the sake of, I'll write the formula for Simpson's, and you can go and repeat that process to find the S sub n on your own. And it's very similar to finding the trapezoid rule up here. Good. So how do we set this up for we want an error of no more than 10 to the negative 3. Well, 10 to the negative 3 equates to 0.001 as a decimal, and we would want to first write absolute value of e to the s is less than or equal to k times b minus a to the fifth over 180 n to the fourth, and we would want that to be less than or equal to 0.001, which is our 10 to the minus 3. So that's how you would set up your inequality to find your n. Good, so we already have the error, and we want that error to be less than that. So we put that above the k. Good, because we don't want the error to be, we don't want that k times b minus a to the fifth over 180 n to the fourth to be bigger than that 0.001, because then we can't guarantee that e to the s is going to be bigger. So we just go ahead and say make k to be bigger, or make k times b minus a to the fifth over 180 times n to the fourth to be less than 0.001. We know what b is. We know what a is. We now know what our upper bound is. It's now time to calculate n, because we also know what k is up here, and our k is 76e. Good. So we just plug in those values there, and we get 76 e times 1 minus 0 to the fifth over 180 times n to the fourth, and that's going to be 0.001. And now we want to cross multiply, so we would get, and this is 1 minus 0 to the fifth is 1, and so we would get 76e is less than or equal to 0.001 times 180 times n to the fourth. And then we would get that n to the fourth is less than or equal to 76 times e over 0.001 times, and we can now, because n is going to be positive, and we're not concerned with n being negative, and so we can take the fourth root of both sides, and so we'll want n to be greater than or equal to the fourth root of 76 times e over 0.001 times 180. And if you give me a moment to calculate, we have here that e is 2.718 if we multiply by 76. We end up with 206.6, and 180 times 0.001 is going to give us 0.18. And we're taking the fourth root of that. So if we do 206.6 divided by 0.18, oops, 206. We end up with the fourth root of 1147.77777, and that's going to be less than or equal to n. And then if we take our fourth root, we end up with 5.82 bigger than or equal to n. And since n is even, we will want to say choose n to be 6. Okay. If we ended up with 4.82, you wouldn't want to say choose n to be 5. You'd want to go up to the next integer that is that big. Good. So those are the two types of ways that you can apply the errors on Simpson's rule and the error on the trapezoid rule. One, you can calculate the error, how much am I off by, or you can say how many n's do I need, or how many partitions do I need in order to guarantee a certain error. Okay, so that does it, and I might do another video